Good afternoon. So before we start our first lesson in the course, let's gather our thoughts a little bit and go over these bullet points to summarize in a way what we talked about in the previous two introductory lectures. Because I want you to keep in mind as we start the material, the main ideas from those examples and keep these in mind. Maybe refer back to this if you want later on. It's not something to memorize maybe, but just to keep in mind for now at least, just to give you a little bit of a motivation of what we're going to do in the class. And I'm going to also write, before we tackle the first topic, also a brief overview of the entire course essentially, or okay, the plan of attack. That is important because you really have to be patient. The nature of the material you'll see is in such a way that many of these things we're going to learn in the beginning of the class will actually be will come together, so to speak, a little bit later in the course. So it may not be really that obvious in the beginning why you need a certain thing to do in order to solve a partial differential equation, a PDE. So the main thing we talked about last time was the fact that general solutions of PDE depend on arbitrary functions, unlike general solutions of ordinary differential equations, which depend on arbitrary constants. So here you deal with arbitrary functions that presumably you need to find them if you impose, as you normally do in real life, if you impose initial and/or boundary conditions. We'll talk a little bit more later on the difference between initial and boundary conditions, that there's a fine distinction there when we talk about the uniqueness of solutions. But like I said before, you can think of boundary conditions as covering everything, right? All the initial data, so to speak, or the data that you know at the beginning of the experiment, so to speak, before you run the experiment, which is described by the PDE, right? The dynamical system, so to speak. Initial usually refers to the time equals 0, but there are other conditions because now the domain is not given by a single variable, right? So just to make it clear here, when you have a single variable function, the domain is basically a segment of a line, right? I mean, an interval, let's say, on the real line, because the only variable is the time. So the boundary of that domain is just the endpoints of that interval, for instance. In the case of a PDE, when you have two or more variables, then any conditions on the boundary of that domain, which is essentially, as the name implies, the region that encapsulates the domain, which could be a rectangle, could be a disk, or many other shapes. Any conditions on that boundary is called a boundary condition. And we'll talk about that more when we deal with the physical, with the PDEs from physics, like the heat equation and the wave equation. So these can be functions in themselves. And then the question is, how do we unify these together? Because at some point you'll have to match this arbitrary function in the general solution with the boundary conditions, which again can be functions themselves. And one way is to basically use a common language or a common way to represent them. And this is given by the so-called series representations. So if you can find series of functions which can represent all these functions involved in the PDE, then presumably you can basically find these solutions and match them with the boundary conditions. I gave you the example from Calculus 2 last time with the power series, because that's an example you already studied in Calculus 2, in which using powers of x, so basically all the ingredients are x, x squared, x third, x to the fourth, and so on in a series. So using series of these powers of x, you can represent presumably a large class of functions. So it doesn't matter whether the function is of an exponential type, or even if it doesn't have a specific form or not. You could use the series representation in place of the function itself. And to anticipate here, the way these series of functions, in solving the PDE, the way they come up to be, or the need for them, so to speak, will become clearer later when we implement the actual method of solving the boundary value problem. The boundary value problem, by the way, abbreviated BVP, is basically the PDE plus the boundary conditions. However, boundary conditions you need in that problem. So this is why you need to be a little bit patient, because it will be a while until we actually get to that point when we actually implement the method of separation of variables. This is the main method we're going to use in this class. Not to be confused, by the way, with the method of separation of variables for the ODEs. It's called the same way because there is a similarity, of course, but this is the main method we're going to use. And in the process of using this method, these series of functions and the need to represent other functions using these series will become obvious as we move along and implement that method. And also the type of these series will be given by the nature of the problem itself. We will start with the so-called Fourier sine and cosine series today, simply because a large class of functions lead to these types of series when you implement the method of separation of variables. But as you will see later in the course, if we change a little bit the problem, then all of a sudden you're going to need different type of series, although with similar properties, but different nonetheless. So not sine and cosine series, but series of Bessel functions, for instance, which we'll study later, or a series of polynomials like the Legendre polynomials, which will be the last topic. So that's the overview from the introductory part of the lesson, of the course, I'm sorry. And let me give you just a overview also of how the course will unfold from this point on. So the order of the topics, this is a general or a rough order, so to speak, because I'm not going to list here all the topics in the course, but the general overview of the topics and their order, just to figure out at what point in the course you actually get to the point of implementing the method of separation of variables. So for quite a while, we're going to talk about the so-called sine and cosine Fourier series. We're going to define what these are, and we're going to basically learn how to obtain Fourier series representation series, so Fourier series for various functions. And quickly, we're going to also learn how to use tables of Fourier series. That's important because in practice, we don't find these series representations by hand. That can be quite tedious and a long process because it involves the computation of integrals. We will learn just for a bunch of functions just to know how this process goes. But in general, later on, we're going to just use tables of Fourier series, and you have to learn how to use the table of some given Fourier series and how to come up with other series coming from those tables. Pretty much like if you remember Laplace tables in ordinary differential equations, when you could find Laplace transform by using various entries in the Laplace table. So you basically combine those formulas to obtain representations for other functions not given in the table. So after that, at that point, we're going to introduce two important equations from physics, like the heat and the wave equation. And we're going to stay a little bit there to understand how these are derived. How do you set up a problem, that is the PDE plus the boundary conditions from a word description of the problem. So we're going to learn how to carefully set up the boundary conditions depending on what the problem states. And then finally, the crux of the main part of the course, we're going to introduce the separation of variables method. And we're going to use the separation of variable method to solve the heat and the wave equation. And at that point, all you studied from up until that point will come together, and then you'll realize why these Fourier series come to be in the first place when you solve a PDE, a boundary value problem. And then from that point, this will be probably around the halfway of the course. The second half of the course will be basically studying different contexts for the separation of variable method. That is modifications that may basically change a problem to the one that you know how to solve before. For example, how you deal with whether the problem is homogeneous or not homogeneous. So there are little adjustments you can make so that you can bring the problem in a form that you know how to solve. But at the root of all, it's still this separation of variable method. And then when I say different contexts, I also mean situations in which you need, like I said before, different types of series. In particular, we're going to talk about Bessel series, Fourier Bessel series, and Legendre. But you know, that's a long time from now, right? That's the second half or end of the course. I just want to emphasize the fact that essentially throughout the course, we're going to focus just on one method only. And if you learn well how this works, you should be able to apply to any problem for which it is suitable. But we're going to keep on using the heat and the wave equation as default examples because they are famous functions in physics, and also they are very useful as default examples to understand the whole concept essentially of the method. Okay, so that's the first page. So finally, there's a lot of introduction in this class, by the way. So that's the way it is. Finally, on the next page, we're going to talk about Fourier cosine series, and then that'll be it for today. So stay tuned for the second page. All right, so we'll start with the definition. We say that a function f of x defined on an interval AB is piecewise continuous if it is continuous except possibly a finite number of points where the sided limits exist and are finite. This is always, as a side note, a funny thing about calculus. I shouldn't write, depending on how you define whether the limit exists or not, I shouldn't actually add the word finite. Because if the limit is infinity or minus infinity, that's lumped, usually, if I remember correctly, in many books under the word doesn't exist. Sometimes I like to specify this because there are many different ways in which a limit may not exist, not just if it goes to infinity or minus infinity. For our purpose, all I want you to do here is to just imagine a function that can only have jump discontinuities. So only jump discontinuities. So to give you an example, typically a function, a piecewise defined function, will be basically continuous over several pieces, right? I mean, it can be discontinuous, but only with jump discontinuities at those points. So for example, you could have a function that looks like that up until this point x1, and then let's say is constant like that up until another point x2 over here, and then let's say then goes like this, and then maybe like that. Okay, so suppose the interval is from 0 to L, just to look at a generic function like this. So f of x on the interval 0L, this is an example of a piecewise continuous function. What I want to point out for our purposes later is that if you have essentially a function like this, which has only jump discontinuities, then you could still compute the Riemann integral for that function. So for example, if I want to compute the integral from 0 to L of this function, all I have to do is to basically integrate the function over each portion from 0 to x1, from x1 to x2, from x2 to x3, and then from x3 to L. So basically it's kind of like as general as it gets, but still ensuring that the integral, the Riemann integral, exists. It doesn't, I mean, it exists in other situations as well, but in this case it's essentially guaranteed to exist, right? Because you have jump discontinuities only. So here's an example of a function which is not piecewise continuous. Suppose, for instance, that you have a function f of x which is equal to 1 over x minus 1 for x between 0 and 1, and 1 if x is greater than 1, let's say. So if you graph this function, notice that one of the sided limits is minus infinity, right? So I mean, it has a vertical asymptote at 1, and is decreasing, right? So if it starts from minus 1, if x is 0, the function is minus 1 over here, goes down to minus infinity, and then it starts horizontally equal to 1 to the right of 1. So that's an example of a function not piecewise continuous. So the reason we started with this definition is because this is basically what the function that you need in order to have a Fourier cosine and sine representation. Because you should remember, we're not going to emphasize this too much right now, or at all in fact, and not too much in the course as well. Remember, when you come up with a series representation, that series, it's not necessarily defined for any x. So just to recall from calculus 1, from calculus 2, when we say that 1 over 1 minus x is equal to this summation from 0 to infinity x to the n, right? So the power series 1 plus x squared plus ... This is true only if x is between minus 1 and 1. So we will expect, we're not going to talk about this too much today, but we will expect that when we come up with a series representation, it's not going to be defined necessarily for every x. So you have to make some assumptions on these functions such that those series are defined. So for now, we're going to assume that these conditions are satisfied. But one of the main ingredients, or one of the main conditions to start with for this function, is that they should be piecewise continuous, and that's why we start with this this definition. And finally, let's move on now with the definition of what we call a Fourier cosine series. So we say that f of x, a function, has a Fourier cosine representation on the interval 0 pi. We can change that interval later, but for now this is the the easiest format, as you'll see. So f has a Fourier cosine representation on the interval 0 pi if f of x can be written in terms of a series of the following functions. So a naught over 2, which is a constant. I'll explain later why you write this over 2, plus a1 times cosine of x plus a2 cosine of 2x dot 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 an cosine of nx dot dot dot. Or, as we're going to write more often in a more compact form, with these terms, a1 cosine, a2 cosine of 2x, and so on, can be grouped into a summation from 1 to infinity, an cosine of nx. So write this down, and if you need, you should pause to catch up. But before we move to the next page, I want to comment a little bit, and then we're going to deal with how to find these coefficients. Okay, so basically, when I say a Fourier cosine representation, I mean that I want the function f of x basically to be written as a combination, a linear combination with coefficients to be determined of the functions cosine of 0 times x, cosine of 1 times x, cosine of nx, and so on. So these are coefficients yet to be determined. Again, the only reason I denote, the reason I denote the first coefficient by a naught over 2 and not just by a naught is just a little gimmick to make the formula easier, as you'll see later. But basically, this is just a coefficient to be determined. And the coefficient for cosine of 1 times x, then we're going to call that a1, then a2, and so on up, and then a and cosine of x, and so on. So just like power series, except that the main ingredients are the cosine functions of 0 times x, which is 1. That's the reason why a naught over 2 is by itself outside of the summation. And then of cosine of x, cosine of 2x, cosine of nx, and so on. Again, a naught, a1, an are to be determined. Right, so that is the main question, right? What are these coefficients so that the function that I start with, remember that's the starting point, can be written in terms of this Fourier series. So with that in mind, let's move on to the next page, and we're going to basically write down a formula for these coefficients. And again, for now, we're going to assume that these series converges. In other words, we're not going to worry for now about the conditions on X for which these series converge. There will be some conditions, but suffices to say actually it does converge for most of the values of the function, with some exceptions, but we'll deal with that later. So stay tuned for the next page. All right, so the goal is to find those Fourier coefficients. So we're going to write down immediately the function and the series representations. But remember, from the previous page, the idea is to find those coefficients such that we have that Fourier series representation for our function. All right, so there is one crucial property that these cosine functions have. Cosine of x, cosine of 2x, cosine of nx, and so on. I really can't emphasize this enough. This basically is the crucial property which will allow you, in fact, to obtain these series representations. And this type of property will follow us in different contexts later. Without it, we can't find these coefficients, basically. So let's go over this property, and then we're going to go back to the series representation and figure out a formula for these coefficients, a naught, a1, and so on. So that property, which is also another way of naming it, is to say that these cosine functions are mutually orthogonal. That property states that the integral from 0 to pi of cosine of mx times cosine of nx dx, so basically m and n again are positive integers, So if you multiply two of these functions and integrate them between 0 and pi, it turns out that the integral is going to be 0 whenever m is not equal to n, so whenever the two functions are distinct, and pi over 2 if m is equal to n. So each time you pick two of them and integrate them between 0 and pi, the product of the two, you always get 0 except when m is equal to n. So let's actually prove this. There is also a homework problem when you have sine and cosine instead. Let's prove this. It's just a basic integral, although we're going to have to use a trigonometric property. Namely, one trigonometric property that we're going to have to use here is cosine times a cosine b is 1/2 cosine of a plus b plus cosine of a minus b. You don't have to memorize this, those of you who take my class, but this is a useful property which will allow you to eventually integrate this product. All right, so let's go over step by step here. If we apply this property here, this stuff inside the integral is going to be 1/2 cosine of m plus n times x plus cosine of m minus n x dx. So we can distribute the integral, and now it's just basically a basic u substitution, right? So m plus n is a constant. The integral of cosine is going to be sine, but over m plus n to account for that substitution. So it's going to be 1/2 sine of m plus n x over m plus n between 0 and pi. And then the second term is 1/2 sine of m minus n x over m minus n between 0 and pi. And so let's be picky here and be careful. Notice as soon as I actually use this property, I have to assume that this is if m is not equal to n, because otherwise I wouldn't have been able to divide by 0. So keep this in mind, because in other contexts, as you move along with the process, you'll realize when you need to actually split into different cases. So right on at this moment when I try to solve this integral, I realize that the case m equal to n needs to be dealt with separately, because obviously I can't move on to this type of expression here if m is equal to n, right? Because it'll be over 0, so that wouldn't make sense. But if m is not equal to n, well, let's plug in pi and 0, so that's going to be 1/2 sine of m plus n pi over m plus n. When I plug in 0, sine of 0 is 0, and then the second term, 1/2 sine of m minus n pi over m minus n, and again sine of 0 is 0. However, remember m and n are positive integers, so sine of an integer, so sine of a multiple of pi is all 0, right? So I mean, if you remember the trigonometric circle, you have 0, pi, 2 pi, 3 pi, you keep on hitting the 2 points for which sine is equal to 0. So sine of k pi is equal to 0 if k is integer, which means both of these terms are equal to 0. So then we just proved that the integral from 0 to pi of cosine of mx cosine of nx dx is equal to 0 if m is not equal to n. Okay, so what happens if m is equal to n? Well, we just have to go back to the original term here. I mean, when we apply that formula, so right here, if m is equal to n, let's just write n instead of m. Then the stuff to integrate is going to be 1/2 cosine of 2nx plus cosine of 0 times x, which is just 1. The first half is the same as before. The integral is sine of 2nx over 2n between 0 and pi, and then plus the integral from 0 to pi of 1/2 dx. And then this is going to be 1 over 4n sine of 2n pi minus 0. The integral here is going to be 1 over 2 times x. That's x over 2 between 0 and pi. Sine of 2n of pi is 0 again, and then x over 2 between 0 and pi, that's just pi over 2, which proves the second half of the property. Okay, so keep in mind these integrals are all zeros. All combinations of these integrals are all 0, with the exception of only one case when m is equal to n. So if you want to pause, do that, of course, as we move along to the next page. But when we move on to the next page, I just want you to pause and pay attention to see how this property actually is essential in finding these coefficients. Later on, we won't do it too often because, as I said before, we get these Fourier coefficients from tables for convenience, but it's very important to understand how these coefficients can be found, because these essential property will follow us in various shapes and forms with some modifications for other types of series later. So that is the essential property, the fact that these integrals are all 0 except the case when m is equal to n. So stay tuned for the next part as we move along with finding a formula for the coefficients of the cosine series. Okay, so how do we find these coefficients so that we can obtain this representation? Well, the idea is actually simple in retrospect, especially because of the property we talked about in the previous page. So let's start by integrating both sides between 0 and pi. Remember, my function is piecewise continuous for over the interval 0 pi. So then I'm guaranteed to have this integral to exist and be finite. So let's do both sides, right? So we integrate from 0 to pi dx. And because on the right hand side we have a summation, we can distribute the integral over each term, right? So basically this is going to be the integral from 0 to pi a naught over 2 dx plus the integral from 0 to pi a1 cosine of x dx dot 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 an cosine of nx dx, and so on. We can do it later on more efficiently by just integrating inside the summation. And in fact, I'm going to do it right now just to get used to the whole concept, right? So basically, with the exception of the first term, if you notice here, I could have integrated the term inside the summation like that. Okay, so if you imagine you have the integral in front of the summation, then you can distribute the integral over each term, which basically is the same as saying you integrate inside the summation. So you don't have to expand the series with dot 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 like I did it here. Then remember, you could always and you should always pull the constant out as a common practice to make things a little bit more streamlined. So a naught over 2 outside the integral, and you're left with the integral from 0 to pi of 1 dx. And in the summation, I can pull an all the way outside the summation as a constant, outside the integral and outside the summation. Of course, not, excuse me, that's a mistake. So outside the integral, because it's still an. I mean, it still depends on n, 1, 2, 3, and so on. So you can pull it outside the integral. All right, so the first integral will be x between 0 and pi. And then sine nx over n, right? So the integral of cosine of nx is sine of nx over n between 0 and pi. So x between 0 and pi is going to be a naught over 2 pi minus 0. And then inside the summation, we have an sine of n pi over n minus sine of 0, which is 0. So pause for a moment and notice that when we integrated both sides of the series of the equality of the function and the series on the right hand side, basically we managed to eliminate all the terms except the first one, because sine of n pi is 0. So basically the summation here is just of zeros. 0 plus 0 plus 0 plus 0 indefinitely. And all you're left with is a naught over 2 times pi. So the idea is to actually use a certain type of integral on both sides, which will allow you to compute precisely one of these coefficients at a time. So you want an integral that manages to kill all the terms except one, and that one that is left will contain the coefficient that you will basically find at this point. So all the terms were 0 except the first one, and all I have to do now is to basically just multiply it by 2 over pi, both sides, and that'll give me a formula for the first coefficient in the Fourier series. Remember, the function is given. The idea is that given a function, how do I find its series representation? So that, in other words, how do I find these coefficients a naught, a1, a2, and so on? I want to point out that, I mean, you will see later why actually it was a naught over 2. It'll be clearer later as we move along with finding the other coefficients. So right now we just found a naught. How do we find the rest of them? Well, I'm going to basically use again the original equality, f of x equals to the series to begin with, and this time imagine you fix n, a positive integer. Basically you do it for 1, 2, 3, 4 and so on. So the idea is to basically find a n when n is equal to 1, 2, 3 and so on. So let's fix one of them. Imagine that n is one of these integers, 1, 2, 3 and so on. And we're going to multiply both sides of the original equality by cosine of nx. So basically the right hand side now becomes a naught over 2 cosine of nx plus a1 cosine x cosine of nx. The second one is a2 cosine of 2x cosine of nx. All of them are multiplied by cosine of nx. Somewhere in the middle, we're going to have an cosine nx cosine nx, and then the rest of them for other values of n, right? So at some point, for example, you're going to have just basically some generic am cosine of mx cosine of nx and so on. So n is fixed, and then you have all the other terms in the series here. So if you again, after you multiply both sides by cosine of nx, if you again integrate from 0 to pi, just like we did it before, this is where the property we talked about came into play. Because remember, as long as you have m not equal to n, so as long as you have all these cosines different, distinct from each other, all of these guys, the integral from 0 to pi is going to be 0, except the one that corresponds to m equal to n. So when I distribute, that's because of the property we talked about before in the previous page. So when I distribute all of these integrals, all of them are 0, except the one when m is equal to n. Dot, dot, dots. And I'm not going to write the rest of them, right? So the key thing is that because of the property we talked about before, so that's n here. All of these integrals are 0, except this one, which is an times pi over 2. Right, we proved in the previous page that the integral of cosine nx, cosine of nx between 0 and pi is 2 pi over 2. This is the crucial property of these. This is the reason why the whole game works. It's not enough to just wake up one day and say, I want a Fourier series in terms of these functions. You need these functions to be also mutually orthogonal, in the sense of these integrals being all 0 except one of them, because this property actually allows you to, in fact, compute these coefficients or find a formula for them. So we obtain that the integral from 0 to pi of f of x cosine of nx is equal to an times pi over 2. How do I find the an? We just basically multiply both sides by 2 over pi. And then an is 2 over pi, the integral from 0 to pi, f of x cosine of nx. So we're going to break it over 2 lectures probably, because I'm going to be mindful of the time as well, in order to come up with an example. So the next thing is to actually use an example to actually find a Fourier cosine series. And then we're going to talk about other properties as well. But for now, let me finish before we move along with why we wrote a Fourier cosine series with a naught over 2. This is just a gimmick to make the formula be the same. If you look carefully here, n, in this last part here, n is from 1, 2, 3, and so on. But if n is equal to 0, that's going to be cosine of 0, which is 1. That'll give me the formula for a naught. So basically, that allows me to write a formula for the coefficients in one place. So instead of using 2 different formulas, one for a naught, one for an, I can just use a single formula and then say that n is from 0, 1, 2, and so on. So if we didn't denote the first coefficient here by a naught over 2, but just by a naught, there will be a missing 2 here essentially. I mean, it will be a different formula basically. So if it was just, let's see, just a naught, it will have been, let's see, just 1 over pi instead of 2 over pi. So it's not a big deal, but instead of having 2 formulas, one for a naught, one for an, it's more practical to have one for all coefficients. You just have to remember that for the cosine series, the first coefficient is denoted by a naught over 2. So you have that over 2 outside of the constant, but it's just basically a matter of practicality. I mean, if you really want to call it a1, a naught, without these 2 outside, then you'll have to basically use a different formula for a naught in terms of 1 over pi. But the convention is to have a single formula. The formula for the sine series looks also very similar, so that's another reason why we have this convention. Anyway, if it's not clear, just ask me during office hours why this over 2 is there. So I think that should be enough for one sitting. The next thing to do is to go over an example on how to compute Fourier series. And that's it for today.